Good morning, champs. Now let's move on to vector surface integrals, or flux. Here we're asking how much of a vector field actually flows through a surface. Think of fluid through a net. If the field is tangent, no fluid passes through. If it's perpendicular, it passes completely. That's why we take the dot product of the field F with the surface normal n. The oriented area vector, r sub u cross r sub v, gives both the size and the orientation of each surface patch. So the flux integral is the double integral over d of f of r of u a v dot r sub u cross r sub v du dv. Notice the contrast. Scalar case uses the magnitude. Vector case uses the full cross product. Now let's compute a classic flux integral. Take the radial field f of xyz equals xyz. We want its flux through the unit sphere, x squared plus y squared plus z squared equals 1. Step 1. Parameterize. Use spherical coordinates. X equals sin phi cosine theta, y equals sin phi sin theta, z equals cosine phi, with phi from 0 to pi and theta from 0 to 2 pi. Step 2. Tangent vectors. Differentiate with respect to phi and theta. R sub phi equals cosine phi cosine theta, cosine phi sin theta, minus sin phi. R sub theta equals minus sin phi sin theta, sin phi cosine theta, 0. Step 3, cross product. Compute R sub phi cross R sub theta. It simplifies nicely to sin phi times the outward normal vector. Step 4 and 5, field and dot product. On the unit sphere, the position vector is already the unit normal. But our field F equals the position vector. So F equals n. Taking the dot product with sin phi times n gives simply sin phi. Step 6. Integrate. Flux equals 4 pi. This matches the surface area of the unit sphere, which makes sense because the radial field points straight out everywhere. So, scalar surface integrals weight surface area by a scalar field, and vector surface integrals measure flux, how much of a vector field crosses the surface. And in our examples, we saw both, a weighted paraboloid area and the elegant flux through a sphere equaling its surface area.